In this video, we will describe an instability phenomenon associated with the strong coupling between a structure mode and the flow dynamics associated with this mode. To highlight this instability, we will characterize the transient flow dynamics associated with an abrupt displacement of the structure along this mode. The need to search for a new coupling mechanism comes from the fact that we are not able, with all the tools we have so far, to explain the now famous phenomenon that caused the fall of the Tacoma Bridge in 1940. Very soon after its inauguration on July 1, 1940, torsional oscillation of the bridge were observed as soon as the wind reached about 50 km per hour. However, the Tacoma Bridge profile is stable from the point of view of drag resist, lift resist, coupled mode flutter, but also with respect to vortex-induced vibrations. We will try to explain this phenomenon by introducing the notion of transient dynamics of the flow. Consider a profile whose angle of attack suddenly changes from 0 to alpha naught. The time evolution of the angle is represented by alpha naught times the heaviside function. If we consider the quasi-static approach that we detailed in session 4 of the course, the lift force follows the same law. That is, Fl is equal to Fl for alpha naught times the heaviside function. All the dynamics of the flow which allows to go from Fl in 0 to Fl in alpha naught is supposed to take place instantaneously. However, in practice, the lift force reaches its stationary value after a path which can vary according to the profile. If this transient dynamics takes place over a characteristic time comparable to the characteristic time of the oscillation of the structure, we are dealing with a complex coupling that induces energy transfers between the fluid and the solid. Let us look at what happens, for example, in the case of a thin profile. After a complex theoretical development that we will not detail here, Theodorsen showed in the 30s that the lift force follows an exponential law and that the characteristic time of establishment of the new lift force is equal to 5 times the time of passage of the fluid along the profile. With our usual scaling, the exponential convergence is written exponential of minus beta URT with beta equals 0.2. Let us see how to use this result to predict the effect of the flow dynamics on the dynamics of the structure. Let us first recall that the derivative of the heaviside function is the Dirac distribution. So the response of the system to this step in displacement is the response to velocity impulse. So we can use a convolution product to characterize the response of the flow to any variation in the angle of attack. In particular, let's look at what this gives for a sinusoidal motion of amplitude alpha naught at the natural frequency of the structure. Alpha of t is alpha naught sine t in this case. The lift force is thus obtained by calculating the convolution of the velocity with the force in response to the velocity impulse. All calculations done, we obtain the sum of 3 terms, the first in sine t, the second in cosine t, and the last exponentially decreasing. This one can be neglected for long times once several periods of oscillations have passed. We find ourselves with 2 harmonic terms. One is in sine t, so it is in phase with the displacement, and in the dynamics of the solid, it can be considered as an added stiffness force. The other term is in cosine t. It is in phase with the velocity, and can therefore be seen as added damping. It is interesting to note here that just as in the previous sessions, the stiffness is proportional to UR square, while the damping is proportional to UR. These added stiffness and damping can be stabilizing or destabilizing depending on the relative position of the aerodynamic center and the elastic center. What happens now if we are no longer considering a thin profile, but the profile of the Tacoma Bridge? We observe that the flow dynamics can lead to transient lift force that are much higher than the lift force at long times. The calculation of the induced forces in the context of an oscillation is less trivial and again reveals, added stiffness or damping forces, which in the case of the Tacoma bridge profile gives rise to instabilities. In conclusion, the dynamics of the flow can itself be the cause of energy transfer to the structure during the oscillation. It is therefore necessary to take this into account when designing civil engineering structures. In this video, we have presented a method to estimate the forces induced on a structure oscillation according to one of its natural frequencies.